Okay, I'm going to make sure that this thing is recording. Yeah, it looks like it is, because I just did a whole lecture where it failed to. Hopefully this will work. Okay, in this lesson, this is 7.1, we are going to get the machinery, the linear algebra machinery, learned in order to be able to solve systems of first-order differential equations. There's lots of different things in the world that can be solved with systems of equations. That's where, instead of looking at just one thing, such as the wind speed or the speed of something, or the solution of something in a tank, or the temperature, you've got two things that you're concerned about. And so in order to deal with two things, you have to have systems of equations, like maybe two different populations. And in order to do that, you need something called eigenvalues and eigenvectors, and that's what we're going to learn about today. So before we do that, actually, we need to do a little rudimentary work in algebra or linear algebra, systems of equations. And so that's what this lesson is about. Basically, this lesson is about theorem 7.1.1 in your textbook, and I'm just going to teach you that, and then we're going to go on from there in the next video. So here's a system of equations, and I meant that to be a 6 and a 17 up here. And I chose the numbers so that it would have this as a solution, 1 and 4. 1 is your x value, 4 is your y value. Let's check it out. If x is 1 and y is 4, you're going to get 2 plus 4 is 6, and you're going to get 5 plus 12 is 17. So there's your solution. So we already know it. But if you didn't know it, how could you go about getting it? Okay, I'm going to show you 4 different ways to solve that system of equations. The first way is something that you hopefully brought with you from algebra. You'll notice that those are both lines if you were to graph them in the xy plane. Then you know that they go through the point 1, 4. So there's the point 1, 4 right there. And this first equation, if you were to solve it for y, you'd get a negative 2x. And so it has a slope of negative 2, and so it's going to look something like that. Okay? That would be roughly the line. And the second one, if you were to solve it for y, notice it would have a slope of negative 5/3. Not quite as steep of a slope, but it's still going to go through that point. So I'm going to exaggerate a little bit, but anyway, it would be something like that. And so they both go through that point, and there's your solution. So if you were to graph them and get the solution, you'd find they intersect at the point 1, 4, and that would be your answer. So that's the graphing method. Let's do another method. Another method is to use what's called elimination, where you get rid of one of the variables. Let's get rid of y, I think would be an easier one to get rid of. We'll multiply this top equation by negative 3, and we'll get negative 6x minus 3y is equal to negative 18. And then when we add these equations together, the y's will be eliminated, and we'll end up with a negative x is equal to negative 1, which means x is 1. Now that we know that x is 1, we can put it in either of these equations. You get 2 here, y is equal to x, 6 minus 2 would be 4. So y is equal to 4. So there's the second method, okay? Those are ones, as I say, you probably brought with you into this course. Here's a third method. A third method is to write this equation as a equation using matrices. So let me write it like this. And in order to make sense of that, you have to first understand how you multiply matrices. Let's multiply the matrix 1, 2, 3, 4, 5, 6. And this is a it has 2 rows and 3 columns. See that? So it's a 2 by 3. And now we can multiply that by anything which is a 3 by something. So it has to have 3 rows, and it can have any number of columns. So let's go 1, 2, 3, 4, 5, 6, 7, 8, and let's just go 1, 1, 1, 1 as our last one. Okay? So how do you go ahead and how do you multiply those things together? Here's what you do. Notice that this is a 3 by 4, and the matrix that we're going to get by multiplying these, first of all, these two have to agree in order to be able to multiply them, and the one that you're going to get as a result is going to be a 2 by 4. So it's going to have 2 rows, and it's going to have 4 columns. So it's going to look something like that. And the way you get each one of these things is by the first entry here. You get the row from this one and the column from this one. So here's what you do. You multiply going boom, 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 and you multiply this, and you multiply this, and you multiply this, and you add them together. So this is going to be 1 plus 10 is 11, plus 3 is 14. So it's going to be 14. What about this one? It's going to be the first row, the second column. It's going to be 2 plus 12 is 14, plus 3 is 17. So that goes right there. What about here? It's going to be 3 plus 14 is 17, plus 3 is 20. Okay, give myself a little bit more room here. And what about the last one? It's going to be 4 plus 16 is 20, plus 3 is 23. So there's everything in the first row. What about the second row? Right here, it's going to be this row, and it's going to be this column. So it's going to be 4 plus 25 is 29. 29 plus 6 is 35. Okay, then you're going to get, this is the second row, the second column. It's going to be 8 plus 30 is 38. 38 plus 6 is 44. Then you have the first row, or I'm sorry, the second row, the third column. It's going to be 12 plus 35 is what? 47. 47 and 6 is 55, if I'm not mistaken. And then the last one is going to be 16 plus 32 is what? 16 and 32 is 48. 48 and 6 is 54, if I did all those correct. So that's how you multiply. That's how you multiply matrices. Okay. So here, if you notice, if you multiply this out, you're going to get 2x plus 1y. 2x plus 1y. And here, if you were to multiply this one out, you'd get 5x plus 3y. 5x plus 3y. And this is equal to this 6. And this is equal to the 17. And so notice that this is just another way of writing that system. Okay, a little more condensed. Okay, what's the advantage of writing it this way? One way is that if you want to use the method of elimination, it's sometimes easier to use it this way than the way I did it before, but we're not going to get into that. Instead, I'm going to show you something called the inverse of a matrix. Okay, so before I give you an inverse, you remember from linear algebra that every metric space has inverses, but in order to have an inverse, you first have to have something called the identity. And I'm not claiming that this is a vector space with multiplication here, but quite often in mathematics, whenever you have one thing, you have the other. So the first thing I need to do is explain what the identity matrix is. So here's the identity matrix. It's the matrix that, maybe as you'd guess just by the name, is going to keep every other matrix the same when you do that multiplication. So this is the identity matrix you get by adding them would be just this one, right? There's the one that if you add this to 2, 1, 5, 3, then you're going to get 2, 1, 5, 3 back again. So that's the identity matrix with addition. But with multiplication, then it turns out that a matrix which has 1s down the diagonal and then 0s everywhere else is going to be the identity. Let's check it out and just see that it works. If you multiply this out, you're going to get 2 and 0 is 2. Then you're going to get 1 and 0 is 1. Then you're going to get 0 and 5, which is 5. And you're going to get 0 and 3, which is 3. And if you were to put this on the other side and do it that way, you get the same thing. So that's called the identity matrix, multiplicative identity. Okay? So once you have the identity, then you can talk about the multiplicative inverse. So what is a matrix that when you multiply it by this one, will give you this one? Okay? And there's a lot of theory here, which I'm not going to tell you. I'm just going to give you the answer. The answer, and I always have to remember myself, the answer is you, for this particular case, it's a very special case, you flip the 3 and the 2 around, and you put a negative in front of each of these. Okay? And that will do it for this particular matrix. I happen to know. Let's check it out. So let's check it out. You're going to get 6 minus 5 is 1. That's what we want. Here we're going to get 3 minus 3 is 0. That's what we want. Here you're going to get negative 10 plus 10 is 0. That's what we want. And finally you're going to get negative 5 plus 6, which is 1, which is what we want. See that? So, so that's the inverse. If we call this matrix A, 2, 1, 5, 3, then the inverse, we write like that, is going to be 3, negative 1, negative 5, 2. Okay? Now, why is the inverse important? Let me show you. What we're going to do is we're going to multiply both sides of this equation by the inverse. And we're going to multiply it on the left. When you multiply by matrices, it's important. You have to be careful about what side you're multiplying them on. If you multiply this one on the left, you have to multiply this one on the left. Okay? They're not commutative the way it is with regular numbers. So let's see once what happens. You're going to get 3, negative 1, negative 5, 2. And the same thing here, 3, negative 1, negative 5, 2. Now we already know what this is going to give us. This is going to give us the identity when I multiply these out. So this is going to give us 1, 0, 0, 1 times xy. And on this side, let's see once what happens. We're going to get 18 minus 17 is a 1. And here you're going to get negative 30 plus 34 is a positive 4. And now, if you multiply this out, you see what you're going to get. You're going to get, well, we already know this is the identity matrix, so if you multiply that by anything, you just get that thing back again. So I can really just get rid of that now. I don't need it there anymore. And so here we have that the vector xy is equal to the vector 1, 4, which means that x has to be 1 and y has to be 4. Okay? So so that's the way to do it with inverses. Okay? So there, that's good. Now the last way to do this is by using something called Cramer's rule. And Cramer's rule is very clever. It says this. It says if you want to find what the x value is, that's the solution to that system of equations, you take the determinant of this matrix right here, 2, 1, 5, 3. That's on the bottom. And I haven't told you what this word determinant is yet, so just hold on. And the determinant on top, what you do is you replace since you're trying to find the value for x, you replace these coefficients, the things in front of the x, you replace those with the solutions here, 6 and 17. So instead of 2 and 5, I'm going to put 6 and 17 there. And then these, that's a 1 and a 3. 1 and a 3. Okay? So that's a bunch of nonsense right now because I haven't told you what a determinant is. Here's what a determinant is. A determinant for a 2 by 2 matrix is just what you get by, let's go 3, 2, 1, 5 as an example. Pretty similar to what I had already. What you do is you multiply these two things together from upper left to bottom right. 3 times 5 is 15. And then you subtract this product, 2 times 1. So that's going to be 13. Okay? So the determinant of that matrix is 13. Let's do a couple more just to practice. Let's find the determinant of 2, 7, 3, 8. Okay? Let's make one of those negative. Okay? So it's going to be 2 times 8 is going to be a 16. And then I subtract. And now what happens when I subtract? I have 7 times a negative 3 is a negative 21. And by the time you get that, you're going to get what? A positive 37. Okay, let's try one more just to make sure you got it down solid. Take the determinant of A, B, C, D. What would that be if you were to actually give the formula? It would be A times D minus B times C. Okay? And by the way, now that I've mentioned that to you, here's the answer for a 2 by 2 matrix. If A is equal to A, B, C, D, then A inverse is equal to, what did I say to do? You flip these two around, so it's going to be DA. You take the negative of these things, negative B and negative C, and then you take that and you multiply it by 1 over the determinant of A. And notice the determinant of this matrix is just going to be 6 minus 5, which is 1, which is why I didn't even have to worry about it before, because that's just a 1 right there. But in general, that's true. Okay? Notice that this also tells us something else, which is very important. It tells us that if the determinant is equal to 0, then you're dividing by 0, which you can't do. And if you can't divide by 0, what that's telling you is that this thing has no inverse if the determinant is 0. See that? A key factor here. A has no inverse. If and only if the determinant of A is equal to 0. When the determinant of A is equal to 0, it has no inverse. If it has no inverse, then the determinant of A is equal to 0. Okay, so that's very important. That's key. Okay, so now that's going to help us out in our last thing I want to mention now here as well with regard to this problem, theorem 711. What if instead of 6 and 17 there, we have a 0 and a 0? How would that change things? Well, we could do it all these different ways to get the solution, but let's just do it the simplest way by using the graph. This one here is a graph that looks like this. A line of slope -2. This one's going to be a line that also goes through the origin, which has a slope of -5/3. Kind of like that. And notice that they meet right there at the origin. So this system right here has a unique solution. See that? It has a unique solution, which unique means one and only one. It has one and only one. Why is that? Because you have two lines that are crossing at just one spot like that. If I gave you two equations of lines, is there anything that could happen other than having one solution like that? Think about it. What else could happen? If I gave you this line and then also this line, then you're going to have two lines that have exactly the same slope, but they have different y-intercepts. They're parallel to each other. There's going to be no solution at all. Let me make sure that you're still with me. Okay, very good. Okay, so there's no solution at all. If I wanted to, I could even make this look a little fancier here. I could make this 4 and make this 2 and make this 6, which is the same equation. I've just changed the multiplied everything by 2, but you still have this line and this line. Okay, notice that they do not have a solution. And also, here's the thing I want you to see. If you were to take the determinant of this system, this thing and this thing, what would you get? You get 2, 1, 4, 2. What happens when you take the determinant of that? You're going to get 4 minus 4 is equal to 0. Aha! That's significant. There is no solution. There is no solution when that determinant is equal to 0. And we already saw that if the determinant is equal to 0, you can't find the inverse, and so you can't find the solution that way, nor can you find it this way. There's no solution to be found. The other possibility is that this you could have an equation like this and this equation. Okay? You'd still get this determinant, but in this case, those two lines lie right on top of each other. So now, instead of having no solution, you've got an infinite number of solutions. Every point along that line is now a solution. Okay? So the moral of the story is this, that the matrix A equals A, B, C, D has a unique solution, which means you can think of it as two lines that intersect in just exactly one spot, has a unique solution if and only if, I'm going to write it like this. I'm going to make an arrow like this. Means each one of these things implies the other. In fact, I'm going to write it like this. If and only if the determinant of A, which of course we know to be AD minus BC, is not equal to 0. So that is key. This thing has a unique solution, means that the determinant is not 0. On the other hand, if the determinant is not 0, this thing has a unique solution. You could also change it around and say if the determinant is 0, then this thing has multiple solutions. Okay, so we could write it like that as well. We could write determinant of A equals 0 means A does not have a unique solution. Okay, so that's going to be key for what we do as we go through the rest of this section. And so I'm going to stop it right there, and then we'll pick up and get into eigenvalues with our next lesson.